So I'm going to present you some results of this European project called the Vinbot. I want to tell you that I'm not an engineer of robotics or things like that. I'm professor of viticulture, so I don't know too much about robots. The thing is, I was involved in this project because I did the viticultural part. But the robot was developed by a Spanish company. So, as everybody knows, nowadays there is an increasing use of robots in agriculture, and there are several applications. If you see the newspapers, the market projections, and so on, they say there is a strong growth predict for the coming years. And indeed, this type of future farm would be in the near future a reality, and Europe are trying to put money on this. So they got this strategic research agenda in order to develop the research in these robotics. That's why today you're going to hear about two European projects about robots. One is this one, and the other one my colleague Javier will tell you later about it. Well, robots in agriculture. You can have drones, and you can have the terrestrial robots. Talking about terrestrial robots, for example, winter pruning. You know, pruning is a big problem to mechanized, because it's a procedure that needs some selection of the shoots and so on. It's not easy to do it by the actual machines. And in order to do a work similar to the one made by man, we need the machine vision to detect the shoots, to choose the right shoots, to choose the right length of the shoots, of the spurs. And this effort has been made. For example, this is an American robot from Vision Robotics, which are developing a robot with some arms that do the cuts almost similar to the ones done by the man. Another small robot, a French robot, is also trying to develop this idea. But you can find other robots, for example, for spraying, for mechanical weeding. This is French products that are now in the market already. To transport, for example, in steep slope viticulture, some robots that can climb the slopes, and for phenotyping, general phenotyping. So here you have 4 examples. Of course, those prototypes are not yet in the market, and I'm going to talk about this one, the Vinbot, and I think that Xavier will talk about Vinrobot. Well, this project aimed to estimate yield. So you know that in viticulture, if you know the yield, that will be a big advantage. So there is a strong demand to improve systems able to estimate the yield. So this is a big list of benefits coming from the knowledge of the yield in advance. So you can plan your crop thinnings, which is an important thing with high production varieties, for example. You can plan the harvest, you can plan everything in the winery. Even you can influence the market, because you can, if we know in advance that we're going to have high yields, maybe the price will go down or the opposite. Even investment and so on. So that's why we'll try to make some yield maps to provide the growers with an important tool. And that was the aim of this project. So it's an autonomous cloud computing vineyard robot to estimate yield and, of course, improve wine quality. The configuration. So there's a lot of sensors, a lot of electronics. As I said, I'm not an expert on this. What I want to tell you is that for image analysis, we use this RGB camera that can detect also the distance from the target. And we use also this laser rangefinder that helps us to estimate, to reconstruct the canopy and estimate some canopy features, some of them that can be also used to improve the models of the yield estimation. Of course, we have RTK, the GPS antenna for the location of the robot. The procedure is in this cycle, so we do the imaging, and then the data is sent to the cloud. Using the GPS, the algorithms will try to recognize the grapes, estimate, in this case, estimate the area, the project area of the clusters, and then transforming that area into kilograms. And of course, given an output to the grower as a heat map, we call it heat map, so this type of maps that shows the variability of the yield inside your vineyard. First of all, we need to detect the clusters. Or if not all the clusters are shown, you detect some fragments. And we do that on both sides of the canopy. For that, there is a complex procedure that I'm not able to talk about. This is made by our coordinator in Catalonia, the Atecnea. They use these convolutional neural networks and deep learning field to detect the grapes and then to do feature extraction and classification and so on. This is really complex for me, and so I'm not going to talk too much about this. One thing that, as I said, we use to complement those algorithms is the use of this rangefinder that enables us to reconstruct the canopy. This is a laser radar, laser rangefinder. And from this reconstruction, you can have an estimation, for example, canopy height, canopy volume, and then you can, for example, calculate the exposed leaf area. As many of you are viticulturists know the importance of knowing the exposed leaf area because it's very well related to the production of quality. And so we can have several features. One of them is also what we call canopy porosity. This is also done usually in the vineyards using the point quadrat method. So we will insert a needle through the canopy, and if the needle finds a cluster or a leaf, we note it as a leaf layer number, for example. If there is nothing, you have a hole. So the fraction of holes you got in your canopy is called the canopy porosity. And with this device, we can obtain this canopy porosity, which is indeed very important to relate with the canopy microclimate and the ripening diseases and so on. But more than that, can be used as an explanatory variable to estimate the non-exposed clusters. And for that, for example, we did some canopy manipulation in order to get a wider range of canopy porosity. So we start with no defoliation, then we defoliate a little bit, and then we did full defoliation in the cluster zone in order to promote a different, a wider range of canopy porosity. So we got high porosity and low porosity. And then we correlated with the exposed clusters, and we are finding some interesting correlation that will enable us to use as an explanatory variable for the situations where we don't see too much clusters. So we can use the clusters that are detected by image analysis, and then using the porosity to estimate the rest of the cluster that are not seen by the image analysis. So this is an approach that I think will be interesting for this. Furthermore, when you got an estimation of the area of clusters by machine vision, you have to transform the area into weight. So we had to do we have done several relationship by destructive analysis using the project area of the cluster and weighting the clusters, and then we did these correlations for several varieties, and as you can see, there is a very good correlation. Could be variety dependent, meaning that we need to have a big library of data from several varieties. It also changed with cluster compaction, so the compactness of the cluster will influence also this relationship. We are trying to understand it better. Then, of course, we produce those yield maps. That's the aim of this project. Well, we validated the behavior of the robots, either regarding functioning and performance in field conditions, several different vineyards with more or less slopes, with the soil management different soil management, so tilled soil, cover crops, and other things. And I have to say that in general, we have a good response of these autonomous robots. But, for example, if we are in slope vineyards with tilled soil, like here, we have problems. We have skidding. So we need to improve the locomotion of the robot in such a situation. So that was one problem that we have to solve in the next prototype. Regarding the accuracy of the algorithms to estimate the yield, you can see here in this plot, this is canopy length. So we estimate per meter of canopy length. So this is one single plant of vegetation, and so this is 16 meters. And this is composed of several plots of 10 meters. As you can see, the pattern is almost similar. So in green, you have the actual yield, and in red, the estimated one. But there are some points that have some not so good adjustment. But if you do the average for all these 60 meters, we got for canopy features a very good estimation. So this is using the canopy reconstruction. So we are happy with the results for canopy reconstruction with this laser. If we put groups of 10 meters together, the accuracy improves. Regarding the yield, so the one that use all the algorithms, even the porosity, we also have reasonable accuracy, but not as good as for canopy features. So we have here underestimate of yield, maybe it's caused by the hidden clusters, and we have to improve those algorithms. So this, the modeling I told you about using porosity and so on needs to be improved in order to reduce this underestimation of the yield. This improves a little bit when we use 10 meters together, because the problem is this point is for 1 meter, and sometimes the image could take the contiguous vines. So that's why when we put together 10 vines together, 10 meters of canopy length, it will improve a little bit the accuracy of the models. Well, that's it. Just for conclusions, as I said, we need to improve the locomotion of the autonomous platform. We need to improve the accuracy, mainly for yield estimation, and the algorithms on modeling and calibration. We are now investing in this problem of cluster occlusion. That is the main problem of estimating yield, mainly in high vigor vineyards, where the leaves cover all the grapes. In Mediterranean vineyards, we have normally some defoliation, natural defoliation promoted by heat stress and the water stress, and we can use those models. But if we are working in a high vigor vineyard with no stress, you cannot see the grapes, which is the biggest challenge of this work. So thank you very much for your attention.